We thank you for the gift. Thank you for the gift of protection that you've given to us. We thank you for the gift of knowledge. We thank you for the gift of everything that you have given in our life, Father. Especially this academics Zoom, which is soon starting our lesson, physics. May you be with us. May you send your Holy Spirit to guide us in all kind of way that you want. I pray this believing in Jesus Christ, our Lord.
Amen.
Amen.
In the name of the Father, the Son, and the Holy Spirit. Amen. Thank you, Stephen, for that prayer I've given us. So today we are supposed to look at something new. Remember last time we did the test and I told members to make corrections. Did you try and do those numbers that were there? Or you didn't do the test?
I didn't do.
Yeah, you didn't do. So why didn't you had not joined, eh? I remember.
I've just joined, sir.
So next time you join.
I found everything.
You found what?
I found out they're doing the exam.
Okay, that's when you found out. So let me share with you the screen and then we see what we are supposed to cover today.
Sir.
Yes?
Excuse me, sir.
Yes, please.
Now, when you says we were the question paper, the past paper.
That past paper is on the website. And you need to be a what? You need to be someone who did the test for you to see that paper. Okay. Get it? So there were questions which were on the website. Maybe at the end, you remind me and I will show you the questions. Okay? All right, so today we are supposed to look at the refractive index, but not this one we looked at it last time, but we look at real and apparent depth. Now, previously, what we looked at here, we are finding refractive index of a liquid, but using a concave mirror. That's the last chapter that we looked at. And we say that the refractive index using the concave mirror is given by n equals to, so we say that shall be given by n standing for refractive index is equal to r minus d out of h. R minus d out of h. Now, what is r, what is d, and what is h? R, this is the distance from the pin to the pole of that mirror, or R is the radius of curvature. Radius of curvature is the distance from the pin to the pole of the mirror. Because this pin here, pin O, is placed at a position where its image is. So if the image and the object they are at the same point, then it means that that point is the radius of curvature. Whenever you place an object and that object forms an image at the same point, then that point is the radius of curvature. So the distance from O up to the bottom here is what we call the radius of curvature. Now, R is the radius of curvature. Then H, let's go to H. This one is the distance between the pore and the pin when the liquid is filled in the mirror. So H is the radius of curvature when the liquid is filled. So it is the distance. Now I don't want to call it radius of curvature, but it is the distance from the pore to the pin when the liquid is filled in the mirror. So this is the distance between the pore and the pin when filled with liquid, filled with liquid. So when there's a liquid that is filled, then we shall have the H, and then D, the distance D is the thickness of that liquid. The distance D is this one is the thickness of the liquids. So is the depth of that liquid, the distance from here up to here, that's what we call the depth, or it is the thickness, or you can call it stroke, you can call it the depth of the liquid. So we use this formula if you want to find the refractive index of the liquid, but using the concave mirror. So that's what we looked at last time. And today we are going to look at so there were some questions which were there. We are going to look at real and apparent depth. There is also this expression which is there, which is NL equals to R minus D over IP minus D. This one is still the same thing, that will still give you the refractive index of the liquid using a concave mirror. Let's pick this one, excuse me. Okay, members, those ones have just joined in. We are just reviewing of what we did last time. So you should know that you shouldn't miss lessons, because when you miss, I don't know whether we shall be going back and forth. Otherwise, if you do that, then we shall not have the progress. So you should always keep in touch and always attend the lessons, and then we move forward. So I've just gone through some of the equations there, and those equations are the ones that we use if you want to determine the refractive index of a liquid using a concave mirror. So the liquid is poured in a concave mirror, and then, sorry, before that you must know the radius of curvature of the concave mirror, and then the liquid is poured in a concave mirror, and then the pin is moved up and down until it coincides with its image here. When it coincides with its image, then it means that that point there, that is the point IP, let me call it IP, or the distance H. In that case, that distance is the distance between the pole of that mirror and the point where the pin has coincided with its own image. So that distance is very important when the liquid is poured there. And then D is just the depth of that liquid. D is the depth of that liquid. So you have to know the depth. How do you determine the depth of the liquid? Automatically, you have to measure the distance from the pole up to the pin, and also from the top of the liquid up to the what? Up to the pin, and then you get to know, you subtract and find the depth of that liquid. So in most cases, if they give you the depth of the liquid, then it's very easy. You just have to substitute in this formula and get the answer, or you substitute in this formula and get the answer. Also, this one, R is the radius of curvature. R is the radius of curvature. And then IP is that distance between the pole and the pin when a liquid is poured, when a liquid is and liquid is poured there, poured in the mirror. And then the other value D, I've said it is the depth of the liquid. So that's the formula that you have to use if you want to determine the refractive index of the liquid. So today we are going to look at, if I make this one very big so that you can see. Today, I don't know who has put this. Maybe that was, that must have been brained, I think. Let me first clean it off. Okay. So today we are going to look at the real and apparent depth. We have already looked at real and apparent depth in our year 1 or in P1 or senior 4. I may say O level because those are something like 3 years back when you start for your senior 4. So real and apparent depth, this is the maybe can I say narrative that we use if you want to determine the refractive index of a given material. Remember that given materials have got different refractive indices due to the difference in the speed of light, or the speed at which the light travels through that material. So if you want to use real and apparent depth, we all know the formula that's given by refractive index is equal to real and apparent over apparent depth. That's the formula that you can use to determine the refractive index of any material, be it glass or liquid. So how would you arrive at this kind of formula, which is here? So we have a diagram which is drawn there. There are some few mistakes which are here that you need to correct in these notes. So I will go through this derivation, and then I'll show you what we need to fix and what we need to leave. So we have that diagram. Heading is real and apparent, real and apparent depth. That's the heading, real and apparent depth, like that. Okay, so we have a diagram there, and this diagram, which is maybe glass, I think it's glass. So they are telling us that there is an it's water, glass, I don't know. I think it's glass. So there's an object, and this object is almost at the bottom here, inside the glass maybe. So if someone is to see that object and that person is somewhere here, the ray from this object will go through refraction at this point here. So we shall have a ray moving from here. I want to draw it like that, that's the ray. Okay. Then at this point here, it will suffer refraction at this point. So we have a normal drawn, and you have a ray. But to draw that, let me first draw this vertical distance here. This vertical distance is going to help us to determine where the image is going to be. So I draw that. So now, if I draw this, I can determine where the image is going to be, because this is the object O. So suppose now it's going to move away from the normal because it's coming from a dense medium to a less dense medium, which is air. And let's say this is glass. So it's going to move away, going to be deviated away from the normal like that, but it appears as if the image is here. So we shall have I there. And at this point here, let us call it B. And this point we call it A. Then someone who's at point C is able to see that kind of ray. So if someone is here by the what do we call it? By the reversibility of light, if this ray is to start from point C then to point O, then it's going to take through the same path, meaning that it's moving from point C to point O, then this angle here shall be its angle of incidence, and this one here shall be the angle of refraction. But reversibility of light, by the reversibility of light, that's what I've said. So you should know that if this angle here is R, then also this angle which is here is going to be R, because these are alternating angles like that. That is R.
Excuse me.
And also if this is I, yes, any question? Okay, I think someone was just sneezing. So this is I
What
also.
clear?
Yes?
What isn't clear to me?
Come again, please. Brenda. Brenda?
Yes, teacher.
What's the question? What are you asking?
Work is not clear. Work is not clear.
So it is not clear.
Yes.
This. Members, are we together? Are you seeing what is on the screen?
Yes,
Yes,
seeing.
I'm saying that.
Excuse me, sir. Excuse me, sir. Sir. May you help us and record the video, sir, if possible? Because some of us are having poor network. Excuse me, sir.
Yes.
May you help us and record the video? Because we are having, some of us are having poor network.
You're having poor network.
Yes.
Okay, let me record it.
Disappear.
I think the lesson is recorded. It is recorded, please.
Okay.
Yes, I think you entered in late, but it is recorded. When you're entering, it asked, it told you that the lesson is being recorded. I think you noticed that. So, so what I'm saying is this, that this angle and this angle are equal. They are corresponding angles. Now, they have said that a ray will be refracted into air along BC. So this ray OB is refracted into air along BC. To an observer at C, a ray BC appears to come from IB. Where is IB? This is I here, and this is B. That's what you should know. There is some light here. It's trying to cover up. Okay, that's what I will do. Okay, so you should know that if we have a ray that is refracted along BC, that ray appears to come from IB as the observer. We watch that. Now, the other thing is that they're saying that O is the apparent position and O is the real position of the object. So that is wrong. So that's the statement that I want us to correct there. That's the statement I want us to correct. O is not the apparent position, but it is I, which is the apparent position. So there it is I is the apparent what? I is the apparent position. And O is the real what? Is the real position of the object. So I is the apparent position and O is the real position of the objects. Now, if you apply Snell's law, maybe at this point here, if you apply Snell's law at point B, applying Snell's law at B, at point B, applying Snell's law at point B, so what are we going to have there? We are going to have, we are going to apply Snell's law at point B, and we shall say n sine I equals to a constant that is a must. To say that, then you have to know that at point B, because the ray is coming from glass going out of air, so we shall say that n glass, then sine R equals to n in air, then sine I. That's what you have to say. Because it's coming from glass entering air, so it is n glass sine R is equal to n air sine I. Then from there, we have to get the value of sine R and also the value of sine I. So we get the value of sine R. So using the triangle, if you can use the triangle OAB. So if we are using OAB, triangle OAB, if we are using triangle OAB, we can determine the sine R. So from there, sine R will be given as AB out of the AB out of OB, isn't it? It is AB out of OB, that is sine R, and then sine I will be given as when you put in the diagram there, it's going to be sine I is going to be AB out of IB. So it is AB out of what? Out of IB. Okay, so that is sine R and that is sine I. So now we are going to substitute sine R and sine I in this expression of Snell's law, and then we are going to get the value of the refractive index. Okay. Okay, I don't know. I think it is not clear. The sunshine is causing its impact, and these are some of the things. Maybe I can do this. Okay, so from here, okay, you want to see this other side? I can show you. Okay, so we have Ng sine R is equal to N A sine I, but sine R, we said it is AB out of OB, which is equal to N in air. N in air is 1. So there I will substitute 1. So it is 1. Then sine I is given by AB, then out of IB, like that. Okay, that's what we have. So the next thing that we have to do is that now we know these are common, those can cancel out, and this is 1. So it means that we have NG times 1 over OB equals to 1 out of IB. So we can take OB the other side, and then NG equals to OB out of IB. But remember, we say that O was the real position. That means that OB is the real depth, and I was the apparent position, meaning that IB is the apparent what? Apparent depth. Okay, so it means that NG equals to real depth, then divide by apparent depth, like that. So there we can say if indeed real depth, if the real depth there was noted as, if real depth was noted as T, if you say real depth is to be noted T, and then apparent depth, real depth is T, and then we can find the apparent depth. Now there's what we call the displacement. Here it is not shown, but there is what we call the displacement distance, or the distance that is displaced. And that distance that is displaced is this distance I, from O to I. That distance there is what we call the displaced distance. So how do we get that displaced distance? D, if I may go back to my diagram here and show you what I'm talking about. We are talking about this distance. You see, this distance here is what we call the apparent depth. Apparent depth. Okay, that's what we call the apparent depth. That distance is the apparent depth. And this distance, which is here, is what we call the displacement, or the, yeah, this is what we call the displacement. I think. Displacement. That's the displacement, and it's noted as D. So how would we find the distance, the displacement D? To find the displacement D, of course, you must know the real depth, and also you must know the apparent depth, and then you subtract. But now if you have the refractive index within that formula, it may be a bit tricky. So we use the formula that you have already derived. This formula, which is here, real depth over apparent depth. So we are going to use that formula, and we are going to determine the displacement D. That displacement is the distance between the real position and the apparent position. The real position and the apparent position. So it is given by okay. So if the real depth is given as T, okay, my camera is not responding. Okay, let me first fix the camera, because you are not seeing what I'm writing at all. But you can go ahead if you know what you are doing. Okay. All right. So this is the real depth. I think let me go back in this other normal method like that. So this is the real depth, which is T. So how do we get the apparent depth? Apparent depth, of course, apparent depth shall be given by the real depth minus the displacement, or the apparent displacement. Now, what is that displacement I'm talking about? That displacement is this distance from I to O. That is the I to O. That distance there is the displacement. So to get the apparent depth, it is the real depth minus the displacement O to I, and you get the apparent depth. So if real depth is noted as T and apparent depth is noted as D, sorry, the displacement is noted as D, then it means that our apparent depth is given as T minus D. So it means that refractive index is given by real depth T then out of the apparent depth, which is t minus what? T minus d, like that. Such that if you want to find that d here, if you want to find that d, this is another formula that you should get familiar with. But if you want to find d here, then make d a subject from this. So I will not do that. That is very easy. You can make d a subject from that, and you have this. It is a walkover. You can practice how to make d a subject, and you have that. So that is some small activity that you can do right now, or you do it later on, and you get your d as t into 1 minus 1 out of n, because I want you also to write something, not to just be there. Okay, they are saying, note, the apparent depth d of an object O is independent of the position O below the glass block. So the apparent displacement d is independent of the position O below the glass block. Thus, the same expression above gives the displacement of an object, which is some distance in air below the parallel-sided glass block. They are saying that this apparent displacement does not depend on the position of the object. Does not depend on the position of the object, or does not depend on the real depth. Does not depend on the real depth. Okay, so does not depend on that position. So it means that it will still give the same displacement for any given object. You will still have the same displacement. You still have the same displacement as long as you are using the same material. You still have the same displacement of that object. So I say that if there are different layers of different transparent materials resting on the top of each other. So here they are saying that if you have different layers of different materials, for example, you have glass, you have water, you have liquid, and those layers of air are resting on top of one another or on top of each other, then the apparent position of the object at the bottom can be found by adding the separate displacement of each layer. So what does this one mean? That if you want to find the apparent position of that object, then you have to get those displacement, but the displacement for each what? For each layer. What are they saying here? So they're saying that if you have, let's say, glass here, if you have glass here, and you have an object at the bottom here, so this glass causes a displacement. So that you have maybe the object appearing to be here, but on top of this glass, there is maybe a liquid here. There's a liquid here, and on top of this liquid, there is water. There is water here. Okay, so it means that there will be different apparent displacements in each of the material. So you have a displacement here, D1. Even here, you have another displacement, D2, and here you have another displacement, what? D3. So what you have to do for you to determine the total displacement here, you have to get the sum of those three displacements, and you get the apparent displacement, the total apparent displacement of that object. Now I'm going to go through just a few examples here. I think just three, maybe number 1, number 3, and maybe the last question, which is number 6 only, and then the rest you be able to do them by yourselves. So let us look at how we apply this formula. So in this number 1 here, they are saying that there is a moving microscope that is used to focus. A moving microscope is used to focus, or is focused on a mark on a table. They're saying that when the mark is covered by a plate, a microscope is focused on a mark on a table. When the mark is covered by a plate of glass 2 centimeters thick, so that means that this glass has a real depth of 2 centimeters. Its depth is of 2 centimeters. This is glass. Okay, and there is at the bottom, there is a material there. So this glass is having 2 centimeters. It's having 2 centimeters, like that. And there is a microscope at the top of it. So there is a microscope. If you put a microscope here, if you put a microscope here, let's say this is where you had put your microscope. That was the initial position where I had put your microscope at the glass block, exactly. But you are not likely to see this object, which is here, when the microscope is just placed on the glass block. So it means that you have to raise. Why do you have to raise that microscope? You raise that microscope because that object has gone through what we call the apparent displacement. Maybe it's apparent displacement. Now the object appears to be where? To be somewhere here like this. And that's where the image of the object tends to be there like that. So it means that now you have to lift the microscope such that that microscope, you move it through the same distance of 0. What? They're saying that the microscope has to be raised 0.67 centimeters from the mark to be once more in focus. So you have to move the microscope a distance of 0.67. So you move a distance of 0.6, maybe somewhere here. This is where now you put your microscope somewhere there. And now it has moved through a distance of 0.67, whereby that distance is equivalent to this distance, which is 0.67, so that you can focus that object which is there. And this distance which is here is what we call the apparent display, the apparent displacement. Are we together? It's what we call the apparent displacement. So that means that if you want to find the refractive index, I've told you that you have to take note of this formula and get used to it. So it's given by T, which is the real depth, over T minus the apparent displacement, where T is the real depth. So real depth minus the apparent displacement, you get the apparent depth. This one here gives you where T minus D is the apparent what? Apparent. T minus D is the apparent depth. Okay, T minus D is the apparent depth. So it's as if T is the real what? T is the real depth. So it's as if it is real depth over apparent what? Over apparent depth. So you substitute there and you have 2 centimeters, then divide by 2 minus 0.67, and you get your what? 2 out of 1.33, isn't it? So 2 divided by that, you get 1 point what? You get 1.5. And that is the refractive index of that glass block. Okay, so number 1 is a bit clear. When you go to number 2, it's still the same thing that you have to use. Now I'm bouncing to number 3 because I'm looking at different categories of these questions. So number 3, they are telling you that it's this one. The number 3 is saying that the tank contains, come on, let's read this question. Let me make it bigger and we see. They're saying that the tank contains a slab of glass 8 centimeters long, 8 centimeters thick. So there is glass, which is 8 centimeters thick, and a refractive index 1.52. That is glass. So glass has its thickness T is given as 8 centimeters, and its refractive index N is given as 1.52. Above that glass, there is a liquid of thickness T, which is 10 centimeters, and of refractive index N water, I think N air, that's the liquid, N air, which is 1.45. That's the refractive index. Then on that liquid, there's water that is floating. So there is water, there is glass now. There's glass, there is water. Now there's glass, there is a liquid. Now there is what? There is water. And this water is floating on the liquid. And they're saying that the thickness of that water, T, is 3 centimeters, but its refractive index is 1.33. So they're asking, what is the apparent position of the mark below the tongue? Are you hearing that statement? What is the apparent? They are not asking for the apparent depth. They're asking, what is the apparent position of the mark below the tongue? That means that from the tongue, what is the apparent position of the mark that is below the tongue? So that means that from the tongue, from the bottom of the tongue up to where you have the image of that object, what is the distance? That's the question. So they're not asking for the apparent depth, but they're asking for the apparent position, for the apparent position D. So as I told you that if you have different objects or different materials which are on top of one another, then you have to find the apparent displacement or the apparent positions of each of them, and then you sum up. So we are going to get the one of glass, we are going to get the one of water, and we're also going to get the one of the liquid, and then you add them up together and get the total apparent displacement. Okay? Are we together? Apire, Stephen, are you there?
Yeah, but your speed is too fast.
Hey, why didn't you complain? I thought you were following critically very well. Okay, members. So let us find the apparent position. So I'll call this one D1, I'll call this one D2, and I'll call this one D3. So D, you know, D is given by T into 1 minus 1 out of N. So I told you to derive this formula. This one is your homework. Go and practice how to derive this. How do you derive this? From the formula of N equals to real depth over this minus D. How do you get this? That's P2 work, which you have to do. So to get the total, we are going to get D1, then plus D2, then plus D3. Stephen, you are saying I'm very fast. My friend, you don't know where you are going. Where you are going. You say, I think the man is just singing. Okay. So we shall substitute for D1. For D1, we shall have 8. That is T, 8 over 1 minus 1 out of 152. Then for D2, we shall have 10. So 10 is out. 10 into 1 minus 1 out over 1.45. Then plus 3 into 1 minus 1 out of 1.33. Here is 10. Here we have 10. Okay. So when you compute that, then you get your D as 6.583 centimeters. I want you to compute it out and get the answer. And then when we come back in the next session, we are going to look at other things. We are going to look at question number 6, and then we proceed.